started. My name is Kevin. I am a co-organizer now of the machine learning meetup. Been a co-organizer for the last 1 or 2 months. So yeah, let's get started. I have a slide to introduce myself. Oh, I just wanna. Sorry. I just want to mention, last time when Bill presented, it was more of an interactive discussion, and I think that I want to keep that environment. There were a lot of good discussions that happened because of it, and that's why over here I'm going to just say discussion led by, because I hope that there's active audience participation. So a bit about myself. I went to school in Illinois at Urbana-Champaign. Both my bachelor's and master's degrees are in civil engineering. I focused on water resources before becoming a data scientist. After school, I worked for the U.S. Geological Survey for 1 year doing rainfall research, and I eventually ended up in a company named Itron. Itron makes electric meters that measure your electricity bill. So we sell those meters to companies, and we are working on apps that leverage the data coming in from residential meters for smarter infrastructure management. So stuff like load balancing, stuff like outage detection, those are the kinds of apps that I work on. And I also had a part-time job for a while. I was teaching data science online through a boot camp named Thinkful. If you are, things didn't go so well. Just if you want to do a boot camp, you can talk to me about it. I probably have some advice for you. And the last time I gave a talk was last year in October. There were like 10 people here, and I talked about my volunteer experience with DataKind, how we used machine learning to predict the complexity of foster care cases so that we could help the organization reduce the burnout of their workers. So 1/6 social workers leave every year, and we wanted to reduce that by making sure that they didn't have too much on their plate. So the motivation for today's discussion, and this machine learning interpretability really is something I have to care about because I work in an industry that's very old-fashioned, right? So I work in the electric utility space, and if you're in any type of industry that people don't trust new technology or are very hesitant to adopt new technology, then you really need to convince them, right? So even if we build machine learning models that can accurately predict the phenomenon we want to describe, utility companies are not going to adopt it unless they really know why it's making those predictions and why, and if it has to in some way align with what their inherent beliefs are. But from a more practical perspective, starting April of last year, GDPR came into play, and as part of the GDPR, people are entitled to the right to explanation for decisions that adversely affect them, like credit or legal. So if somebody's denied a loan, they should be able to go to the company that denied them the loan and ask for reasons why they were denied. And this is something that's becoming more and more into play. So as data scientists, we should learn, how we can describe our work and how we're generating the decisions that we're making. If you have any questions, just raise your hand. So use cases of this. So number one, of course, is if you do like consulting or you're client facing, you can earn more trust by describing what goes on in your model. But besides that, there are other use cases. Like for example, you can predict when your models will fail. So let's say you're building, a neural net that deals with self-driving cars, and part of it is you need to identify the bikes. if you build a classifier to identify bikes on the road, and you open that classifier up, and for example, you're only seeing like wheels of the bicycle, then in scenarios where the wheels are blocked, your classifier may fail, the bicyclist may get hit. So if you can preempt these scenarios by checking what your model is seeing and what your model is using to make decisions, then you can adjust, you can maybe change your model, you can tweak your model to avoid these cases from happening. And part of this is the fact that when we train our machine learning models, these training sets are normally cleaner, and they sometimes don't include real-world outliers that can be the edge cases where our machine learning models fail. And so, for example, like if you are predicting, something that relies on people's income, and maybe in your data set, income only, in the maximum value of income you have is $500,000, and then somebody comes with $1 million income, and you have to predict that. You need to know how your machine learning model will respond to inputs beyond the scope of what you saw in your prediction, in your training set. And one of the more practical applications of this is recourse analysis. So recourse analysis is kind of prescribing what steps could have been taken to avoid this prediction, right? So for example, we deny somebody a loan, and we need to tell them what they can do to improve their credit or their financial standing, such that we can approve the loan. So for example, we can say you have too many credit cards open. Maybe if you reduce the credit cards that you have open, maybe we can grant you the loan. And similarly, we can do preempt cases. We can defend against adversarial attacks. So adversarial attacks are, for example, some guy knows he's going to be denied a loan, so he'll just cancel the second credit card that he has open, and then after he gets the loan, he'll reopen that second credit card. So stuff like that. We need to know what kind of tweaks people can do to kind of fool our model and sidestep it to get an advantageous prediction. So in preparing this lecture, there was one standout resource that I want to mention, and there is a book on interpretable machine learning. It's not that long, and yeah, I strongly suggest reading it if you're more interested in the topic. So this is a famous scenario from a paper published in 2016. Basically, they got 40 images of huskies and wolves, and they're trying to predict which ones are huskies and which ones are wolves. And the classifier predicts 5 out of 6 of the scenarios correctly. So the bottom left one is it predicted wolf, and it saw husky. And if you look at the explanations of why it made these predictions, so the predictions are on the right side, you see that one of the major factors of making a prediction is the snow in the image, right? So we don't actually have a husky versus wolf classifier. We just have a snow detector that we're using, and that's why the bottom left image is failing, because we have a husky with snow in the background, and it's predicting it as a wolf, but it's actually a husky. And also, AI is being used more and more in legal and financial decisions. So I got this I saw this article from earlier this year, and so they are using machine learning to create a score for a person, and the score is whether or not the person's likelihood to reoffend. So, if the person goes to prison and he gets out, what's the likelihood that he'll go back in? So recidivism. And so this score is actually important in sentencing, right? Because if you feel that the person is likely to reoffend and go back into jail, they're more likely to get longer sentences, jail time. And if you feel that, oh, he was a standout citizen, he just messed up, then you're likely to reduce the sentence. So there are AI systems coming into play. So the reason why this article said us getting it wrong is because historical data, of course, is very biased against low-income people, maybe biased against people of certain race. And if you use these features to make predictions, then your model is using kind of biased information, or you may reinforce the bias present in society, and by reinforcing this bias, you continue to hurt vulnerable groups. So this is something we need to be careful of. So in general, in the machine learning space, I doubt you can read the slide, but basically this is a graph of complexity versus interpretability. And at the bottom right, we have our linear so at our bottom right is the most interpretable, least accurate. So y-axis accuracy, x-axis interpretability. And on the bottom right, we have our linear regression, logistic regression. So simple models, not the most accurate, but highly interpretable. And then we have decision trees as we climb up. Decision trees are more complex, but we can still interpret them. And as we go up to ensemble models, or even the kernel-based models like support vector machines and neural nets, we lose a lot of interpretability, and we don't know why these predictions are being made, although they perform the most accurate. So there's a trade-off we have here as data scientists. Sometimes there are some applications where you don't need the model to be interpretable, but you need it to be accurate as possible. So you sacrifice that trade-off, and you aim for those neural nets and stuff. But there are times when we need highly interpretable models, and we can make that trade-off of sacrificing a bit, going down to decision trees, and maybe using that as our model because we can explain why it's making those predictions. So before we go on into ways how to evaluate, how to interpret those more complex models, we'll start with the simpler models because these are the basis for interpreting the more complex models. So we'll tackle for here just linear regression, logistic regression, decision trees, and k-nearest neighbors. So questions? None? Okay. So first for linear regression, right? We just have coefficients times the values, and we can see the model importance given the t-value, right? So this is something we can, as long as our coefficients are normalized or our values are scaled well, we can see which features are the model are stronger for the model and which features are not so strong. So this is a plot of comparing two linear regression models. This data set is it's in R. It's the state X77 data. So what it is, it's all the states, and it has metrics for income, murder rate, illiteracy, etc. And this regression is predicting income versus frost, so the amount of snow, illiteracy, murder, and the rate of people graduating high school. And you can see because illiteracy is inversely correlated with the number of people who graduated high school. When we introduce this feature into the model, the weight on the illiteracy feature goes down. In practice, I read that, so look at frost, frost is not so important in determining the income of a city, so it's a very weak feature, closer to 0. And on the left and the right bars are our 95% confidence intervals. So if we have a feature that's very close to the 0, that means it really didn't have impact in our model. Questions? No? Okay. So, and this kind of illustrates one of the weak points of linear regression, right? In that when you introduce correlated features, the weight on those features gets split. So even though illiteracy by itself is a good indicator of maybe our income, once we introduce the high school graduation rate, the signal gets split among those two features. And with linear regression, we can plot the effect plot also. So we have, on our y-axis is what we were predicting, income, and on our x-axis is illiteracy. And we can, the points are the individual values that we saw in our data set. So we can kind of see, because we're doing linear regression, we draw our line of best fit, and we can see the relationship between illiteracy and income, and we can see that it somewhat captures the signal reasonably well. And the gray section is our error bars, or what do you call it? It's confidence interval around the predictions that we made. So advantages of linear regression. One, it's highly interpretable, but we need to handcraft features. It can't detect feature interactions on its own, and it tends to give worse results whenever there's correlation within our features. So second, we're going to discuss, linear regression was very easy to interpret because one unit change in an x variable corresponds to the same y unit change in the y variable throughout the values of the x, throughout the whole distribution of the x, right? So it's monotonic, it only goes in one direction, an increase in this x variable is also an increase in y, etc. So, but with logistic regression, because of the sigmoid, first we have the sigmoid function on the top, and if you're unfamiliar with the sigmoid function, right, it has that curve, so it's meant for classification. It goes, the minimum is 0, the maximum is 1. And the way to interpret logistic regression is after enough math, you can arrive at this equation here where we deal with odds. And the difference between odds and probability is, I have it in a slide later, but basically odds are the ratio of your positive event happening to the negative event. So if I am predicting like a coin flip, heads and tails, and heads is, let's say heads is the positive, tails is the negative, then my ratio would be 1:1 because I have a 50% chance. If my coin were weighted and the chance was 75% of getting heads, then my odds would be the 0.75 to the 0.25, so my odds would be 3. So the coefficients in logistic regression affect the odds. So this is the graph of odds versus probability. So you can see as probability approaches 1, odds is going to go up to infinity. Any questions with this one? No? Clear? I hope so. Just personal anecdote. When I hear stuff like, you hear stuff like, oh, there was a drug trial and this drug has like a 5-time, people who take this drug are 5 times likely to survive, right? Some people say that that's just wrong English. I think in some cases they're referring to the odds, right? So going back to our scenario where we had a 3:1 chance of a positive event, the 5 times of those odds would be the 15:1 event, right? So that would be around the 94%. It would be like, it would go all the way up there. And the reason why we need to know odds is because our weight, going back to the equation here, where we have a coefficient, so we have e to the b, is directly proportional to the odds. So when we have a weight, when we perform our logistic regression and we have weights, we raise that, so we do e to the weight, and then we get the odds ratio. So this means that, for example, this smokes, yes or no. It means that if the person smokes, then there is the person is like 0.77%. So we likely
more likely to, this is contract cancer. So in general, like, I think this is specifically cervical cancer. So like, for example, hormonal contraceptives, they increase the likelihood of developing cancer because the odds would go up by a factor of 1.12. Clear? Okay. K nearest neighbors. This one is very easy to interpret, right? Because our predictions are just based off the neighbors. So we can easily zone in on one observation and we can say what were the neighbors that influenced this decision. But the interpretability of this model is only on a local level. We can only do it one explanation at a time. And if we were to discuss why, what make on a global level, on the whole model, on all our observations, we couldn't really extend the local level to that global level. So we can only interpret on that local level. And then next, decision tree. So decision trees are inherently interpretable, right? Because you can easily visualize them. You train one classifier and you can easily say, okay, what were the features, like what is the root feature, so that definitely corresponds to a very strong feature, and you can kind of see how you arrived at a certain decision. So to interpret these, you would just really just visualize them, see how observation went through. Advantages of decision trees. So number one, right, it can capture feature interactions. It can say, if feature X is greater than 5, then we can check if feature 2 is less than or equal to 1, etc. And we can model those interactions. And then disadvantages, unstable means the model that which it converges that can easily change depending on the input. If we knock out like 5% of our rows, we can easily arrive at a very different decision tree. And lack of smoothness, because it has to make cuts per feature, it cannot really model any linearity, right? It has to always create these cuts. And it can be very inefficient. So after going through the more interpretable models, these lower accuracy, I'll go over gradient boosting. Who's familiar with gradient boosting? Okay. So gradient boosting, right, is similar to, the base unit of it is decision trees. The concept is that if we get the ensemble prediction of a lot of these small unit, these weak learners, then we can create a strong prediction. So we have a lot of weak decision trees that are very shallow, and once we ensemble them, we create a better prediction. So these decision trees, these weak learners, are made in a sequential process, each one building over the last one and creating a better decision tree each time. So we'll get better over time. And once we start to increase the complexity of the model, things start to get less interpretable. So as an anecdote, I had to use this at work. So first, I had this problem at work. I had to model it, and at first I was using the interpretable models because, that's what my boss told me to do, really. But after I moved to the more complex models and had that higher accuracy, then he was more open to using the more complex models. But again, he was asking me, how do we interpret these? And if you're familiar with using XGBoost, you can get feature importances, but secondly, you can get, so there are 3 types of feature importances: cover, weight, and gain. Cover means how many trees did our feature appear in, and gain is the one that most corresponds to our output. So we can say that this feature 18 at the top with really high gain, if we take it out, our output will really our accuracy will really suffer. And I think weight is related to where in the tree it lies. You can correct me if I'm wrong, if anyone knows. But what happened is, I didn't know which one to give my boss, right? And I gave all three. And that just confused him even more, because even though they're from the same model, you can see that they don't give the same results, right? So they rank features differently based on the three criteria. And basically my boss went back to me kind of questioning if this was even reliable. And that has been one of the criticisms of the current, ways we look at feature importance. Mainly the fact that it is inconsistent. There are many ways to look at it. And this is why there have been, efforts to develop more methods that are more consistent, more reliable, and make more sense. Before I go to more model-agnostic approaches to interpretability, I just wanted to bring up this package. So there's a package in Python called ELI5, and basically it makes an API for all scikit-learn models that you can easily just say show weights, show prediction. So if we go back to our linear regression and we show the weights, it will show the weights for us. If we say show prediction, we feed in an input and it'll show us why it made that prediction. And they extended this API to gradient boosting, so your XGBoost, your Light GBM, your Cat Boost, they all have this now. So it works for pretty much all your standard models, and you can just call the function show weights and look at what your model saw. So if you have multiple models, you can just feed them in. And then so show weights just takes two parameters. The first is the model, the second is the dictionary of feature names. This is the Titanic data set. So here, you're predicting whether or not a passenger survived. They prioritize females and children, so we can see that female is a very strong feature. And then second, you can use it individually, right, on an individual prediction. And the score, so there's a probability given and a score. The sigmoid, if you pass the score to the sigmoid function, so 1 over 1 plus e to the score, you'll get the probability. So this is how it made that prediction. And because our probability was over 0.5, we deemed it as a yes, they will survive the Titanic. So here you can see the features that contributed to this decision. The passenger class is the class of the ticket. So there's three classes: first class, second class, third class. So obviously the rich people have a higher chance of being saved also. So because this person was a female, they got that positive contribution from it. But then because they were in class 3, there was a negative contribution. But overall, it looks like the prediction was that this person survived. So with that, we already covered all of the model-specific ways to interpret features. Model-specific ways for interpretability. But more recent research has been asking the question: how do we create model-agnostic approaches? So whatever the model is, a neural net, a gradient boost, or decision tree, how do we perturb the inputs in a way that we can see the outputs and make an evaluation based on that, right? So the first one is partial dependence plots. And basically, it'll probably make more sense if we just look at it. So this is a partial dependence plot. The y-axis is the strength of concrete, and on the x-axis we see features. So on the left side we see cement, on the right side we see water. So if you notice the linear regression, here is just a straight line. So what happens here is, for example, for cement, our values range from 100 to 600. What we do is we grab the value 100 for all our model input, for all our data observations, we change all of the values to 100. we get the average prediction. And then we move to 200, we change all the model inputs to 200 for cement. We see the output average, and then that creates another point. So one of the parameters when you use this approach is the grid size. How many of these points do you want to calculate? And obviously, the more points you include, the more expensive and the more time it takes. So what's noticeable here is that we have these blenders. We can have model ensembles, and we can still use this approach. And here we're comparing the effect of cement on the strength. So the linear regression will be straight because that's how it was modeled, right? So if we get all our input changed to 100, 200, we'll just come up with a straight line. Whereas the other models will come up with these weirder curves, especially there if you look at water, right? Where there's this non-linearity around the between the 120 to the 180, if you can see. So with these types of plots, we can kind of see, how our model interacts with the features. What happens? We can even, hypothesize what happens if there was a cement value of 700, and we can see how our model will treat that and what kind of prediction our model will make. So going back to the equation, this 1 over n just means, so xs is the feature that we want to isolate the effect of. Xci is the other features. And we want, if we get the summation, so the f hat is the model that we have. So we're passing in the model, the data that was trained on. And if we get the average of that by when we isolate for each xs, then we can see how each feature, we can estimate the effect of each feature on our output variable. Clear?
So this assumes certain independence of the variables. Like say cement, like doing this. I mean, if cement correlates to something else, right, which you're not biasing.
Yeah.
You won't be seeing here.
Yeah, so that's one of the main flaws, and there are efforts to correct that later on. So we can also do this plot in 2 dimensions. So this was the cervical cancer data. So on the y-axis you see number of pregnancies, on the x-axis you see age. And one of the suggestions in using these approaches is because when we look at this and we're actually feeding in the inputs, we don't know if those data points actually exist, right? Maybe there were actually no cement values between 350 to 450, but in order to create this plot, we are assuming those variables and passing them through. But it could also happen that those variables actually don't exist in the model. So one of the things you can do is you can see the rug, which indicates the density. So for here we can say, so this is 2 variables, and we're seeing the chance of them getting cervical cancer. So you can see here, if they're around the 40-year mark, they had a high number of pregnancies, they're more likely to get it. But then it seems around 60 to 80, our predictions we're not predicting a high likelihood. And if you look at the data, it's because we only have like 1 point, 2 points, 1 point. So it's making unreliable predictions when it hits that side, because it's passing data that doesn't actually exist into our model to get those outputs. Same thing here, right? These are not dense, these number of pregnancies, these 9, 10, 11. So our predictions will be more unstable at that point. So one of the interesting applications I saw was you can compare, right? So this plot here is the probability a basketball shot will go in depending on the distance, right? So you can see how each model treats distance as a variable, and you see, like, for example, the random forest has a steep drop off. After 30%, after 35 feet from the basket, it's not going to go in. And then you can evaluate, there's very low likelihood. Whereas the other, let's say this neural network, it's asymptotic around this point. So now you can evaluate and see how your models will perform when it has outlier inputs going in, and you can decide which models you want to keep based on this. So if you prefer the interaction where it just drops off, then you would keep your random forest. If you prefer that asymptotic, then you would keep the neural network. So yeah, advantages. This plot is very easy to interpret in a sense that you just see a graph, you see the dependence already. Disadvantages, you can only do it one feature at a time, 2 features maximum. And again, it interpolates in areas where you don't have data. As Anton mentioned, it assumes independence. And then it can, we'll discuss Hyde's heterogeneous effects. So, this is an example of a heterogeneous effect, right? Wherein we have feature, we have a feature x2, and this data obviously has 2 clusters. There are 2 ways that the data can interact with feature 2, right? So there's an if-else kind of break here. One cluster sees it as is positively has a positive correlation with it, and the other one has a negative correlation with it. And if we were to use the partial dependence plot, wherein we say let's feed it all the values are -1, and then we get the average, we land on this line. So this is the partial dependence. And what you can see here is that we don't capture this feature interaction. What happens is it gets averaged out, and we see it as having no dependence, even though there is some. This is a very extreme case, and this is fake data to show the weakness of the partial dependence plot. In reality, these types of data sets don't really happen so often, wherein you have 2 clusters and they behave very differently with the data. These if-else breaks. So, in order to get more resolution, what we can do is we can do the partial dependence plot, but we do it for each observation. So, for example, we say this observation, this one here, we will replace the value with age equals 20, then with age equals 21, 22, so on, until we get here. On the right side, our predictions are less accurate because we don't have data there. So it's not really modelable. You can see by the rug. There's a lack of data. So if we trace each one, if we do it on each data point, we can graph how each data point's prediction has changed based on how much the age changed in this graph. And we can see that there's all sorts of interactions, but in general there is a common trend where at a certain age it just spikes up and then dips down later. So there's a common shape here that we can see. And you can combine the previous plot and this plot, so you can combine you can zero center it, and then also, so if you zero center your individual condition explanation plots, you'll all start at the same point, and you can track that up and down so that you can see, and this just makes things easier to visualize compared to the previous plot, where it can be all over the place. And if you can plot this partial dependence plot in the middle, and that's the average of all the contributions. So in general, they are the same computation, same expense computationally, but it's just a matter of how you're presenting the output. So advantages, we get more granularity into how our model is behaving, and then we can uncover heterogeneous relationships. And then disadvantages, it's a pretty crowded plot, and we can only do it one feature at a time. Questions? No? So yeah.
So yeah, right.
Oh no, I'll get to your point. You have the same point? Oh no.
No, so for each observation right now, which can have, say, I don't know, like 40 variables. We're just picking the variable age and we're changing with the variable age. Is this correct? Or?
Yes, that's exactly right. So we isolate age, we're just changing age, and we're seeing how our Y value changes. So we don't know what the model is, we're just changing age, we pass on the data into the model, we get the corresponding predictions, and we can kind of see how the predictions depend on a certain variable, and we can capture non-linearities in this way. So even if you have like a neural net or something like that, where you don't really know what's going on inside, you can still use this process. We'll get one of the initial features before transformation, before anything, and plot the dependence of the output on that. Clear? Okay. So now to Anton's point, where we have what do you call this? Correlations between variables, and that's what you can see here, right? Where we have x1 and x2. These are features in our model, and they're very strongly correlated. And if we were to use the partial dependence plot, so for example, we say, hey, we're gonna get all our data and fill it with x1 at 0, and then x1 at 0.25, and then at 0.50. We're gonna get values of x2 that are impossible. We're gonna get value pairs of x1 and x2 that are impossible, right? So, for example, x1 is 0.5 and x2 is 0.5, and we get that data point, and we change x1 to 0.0. Then our point will be here, where x2 is 0.5, x1 is 0, and then so the message here is that the point doesn't really make sense, and it's kind of wrong to evaluate our model using a nonsensical point that won't exist. And one of the main, one of the common examples here is height and weight, right? Like if a person is like 6 feet tall, we're not gonna assign them a weight of like 80 pounds, right? So we need to keep the dependence in some way. And because in the previous two plots I showed you, for a person who is 6 feet tall, we're gonna keep that 6 feet tall, and then they'll go through all the different weights possible, right? And same thing for all different weights, they're gonna go through all the different heights possible. And that's gonna lead to some weird features. So a good example is like if you're predicting housing prices, and your housing prices are dependent on floor space and number of rooms, these two features are very correlated, right? So the more floor space you have, the more rooms you have normally. And then you're gonna run into testing scenarios where you have an insane amount of floor space but only one room, and then same thing, a small amount of space and 10 rooms, right? So we need a way to correct for this, and that's what the accumulated local effects does. So we want to capture the distribution at this point. So we say, what is the conditional distribution of x2 given x1 is this line 0.75. And if we go back, this is the problem that arises with the partial prediction plots, right? So as a thought experiment, what the author did here was he created a model. This model pretty much linearly models this, except this point here, wherein if he reaches this point here, it's just going to assign the maximum value. And the reason this works is because our data only lies along this line, meaning that our metrics, in terms of our R-squared, in terms of our mean average error, they're all going to look right, but we won't know about this space where our models fail pretty bad. So if you were to go to this kind of data and plot your partial dependence plot, what you're going to get are plots like these to the right side, right? Wherein you have these really weird spikes, and then it fixes itself. So if we somehow accounted for the distribution of x1 and x2, realize that they're well correlated, and we perturb our data in a way that accounts for this, then we can avoid the partial dependent plots that look like that. So here is the same data, but we accounted for local effects, so we can see that we get straight lines, because now we're only testing data points that actually exist. So the author of the book actually says that he would use accumulated local effects over partial dependence plots for all cases. The only downside that I saw was that it's harder to find packages that do these, the partial dependence plots are way more common, are more unified to APIs, to like in Python, to all other models, you know. So in general, this package is harder to find. So in practice, what you would do is you would just you create grids, you grid your data, and in this particular case, we're gonna go to this section, and for data points that lie in this grid section, we're gonna move the points to the minimum and to the maximum, and then we can see the difference of the effect when. So for example, if x1 is z4, then we get all the values there, we average it out, and we subtract it by all the values at when x is replaced by z3, and then we can get that marginal increase that's of our y variable based on our x variable. Does that make sense? Okay. So this takes away the bias, right? So this is unbiased. It's faster to compute because we're only practically predicting on points that exist. The only downside is that we need more points, a lot of more samples per bin, and there's no really good way to bin because a lot of times, especially if your data is kind of normally distributed, your tail bins can become very sparse. So that's a downside to this. And then of course, there's increased complexity in the approach and in looking at these plots.
And if you have a correlation, I mean, if you have like more than two variables,
Yeah.
you'll get the curse of dimensionality very quickly. In a sense, you don't have enough points, which is something you mentioned in one of the slides here. You just, you know, if you imagine you have 3 or 4 variables and they're all correlating, they're making some plot. But with you're using the binning and using this Cartesian kind of product distribution, not distribution, separation of the space. You'll have a very small number of points in each of the cubes or each of the cells of the bins. And this, I mean, this is a serious limitation to this approach. And you need to have much more data.
Yeah, so what Anton is saying is that if you have a lot of variables, there are some variables that you'll have very limited combinations of, and because of that, because you use this binning approach, you're gonna have a very small sample in some of those bins, and that is one of the weaknesses of this approach. Yeah. And then a more simpler approach is the global surrogate model. So this is used in like your sciences like physics, chemistry, etc. Where if you have something that a function that is very expensive to compute, what you do is you create a simpler function that approximates it. You know, maybe we can't get that. Maybe we can do our predictions 100 times faster, and maybe the R-square agreement is 0.9, you know, 0.92, etc. So maybe we can replace the more complex model with the simpler model, in the hope that we can make predictions faster. So in our case, in model interpretability, for example, you have a decision tree that goes down to has a depth of 8. You can replace that with a simpler decision tree with depth 3, for example. And as long as the two R-squares are reasonably similar, then you can say that your simpler, more interpretable model, it can approximate the effects of your complex model. So this is very intuitive, but of course, if you have perfect R-square, like they perfectly match each other, then there's no reason to take the more complex model over the simpler model. So at that point, you would just replace your complex model with the simple model. And the thing to point out here is that your surrogate model never sees the original data set, right? The surrogate model only sees what predictions were made and is basing its performance off of the predictions that were made, right? So there is some error already. So if your first model doesn't even have a good R-square, maybe there's no real value in doing the global surrogate where you get a simpler model. Okay, now we're moving on to more advanced approaches. So the line paper was published in 2016, or was in NIPS 2016, and basically, this is an image from the paper where we have a really complex space. And of course, there's just no way that we can simplify the interpretation of this model. So what Lime does, so local means it focuses on a single point, model agnostic, so it can work for any black box model. And what the goal is that it will zoom in at a specific point, just one point, and then it perturbs the data in a way and creates a linear model at that level that is highly accurate. So just for that local boundary. So in this case, we went in here, we sampled points around, points closer to our point, weight our linear model more, points further away are weighted less, and we create that linear model that explains this boundary. And if we do this local boundary, we can look at the weights of that linear model, and it would give us an explanation to what our model's doing. So here's the formal steps. So for each prediction, we perturb the data n times, you choose n, and then we calculate the distances from the perturbations to our original data, and we weight them with a similarity score. So you can decide how far away your model should look, what kernel to use, and you can also determine what similarity score to use. And you select the best M features that describe your model. So normally you would limit this to like, what are my top 4 models, top 4 features, top 5 features in the linear model. And you would say that that is the description on the local level. There are also approaches where instead of a linear model, you could use a lasso regression. So if you had 100, 200 features, you could easily get what were the strongest 5 or strongest 10 by regularizing the coefficients down to 0. So you can, there's a lot of freedom to choose what model you want to use on the local level. And this is the output of the Python package. So there are two the first caveat to using this is that things need to be label encoded. So if you have a class, for example, here are male, female, we have to label encode that. And the reason is that when Lime perturbs data, it has to perturb data in a reasonable way. And if you one-hot encode your variables, for example, the season of the year, winter, spring, summer, fall, you have 4 columns. The way it perturbs data, you can have fall and winter at the same time, fall and spring at the same time. And in order to avoid this limitation, what they required is that your data has to be label encoded instead when it's passed on to Lime. And this kind of personally creates some kind of difficulty manipulating the data, because the data is not exactly the same as what was fed into the model, especially if I'm using one-hot encoding into the model, right? I need to manipulate my data again to pass the label encoded version. So here, right, we see the prediction probabilities. Here, what were the features, and then it breaks your data down into quartiles. So this is like the passenger class, was less than 1, so it adds this much. So here you can get a kind of a feel of why this prediction was made because of the linear model. And this is just another example of poisonous mushrooms. We have categorical data. The odor was foul, etc. So we can, and on the right side is what was the actual data that was observed. So the right side is the raw data, this feature importance, and this is the prediction. Sorry. So if you do this enough times, they have a framework in the same paper called SP-Lime. And what SP-Lime is you give it n number of points. You say, I want to perform Lime on 100 points of data. And it goes through 100 points, permutes the data, creates a linear approximation, And then what it does is it wants to get non-redundant examples that kind of describe your global boundary. So if you look at enough local observations, you can kind of get a feel for what's going on at the global level. So this is an example of that, where we fed it into SPLime, the Titanic data set again, and that it gets 4 points that it thinks represent the boundaries at the global level. Questions? No? Okay. So one of the cooler applications of Lime that I found was, it seems a lot of people are applying this to text data, because here we have an example of atheism versus Christianity classifier, and we can actually, this is with the package also, we can highlight the specific words that caused us to make a prediction. So for example, in this email, if we look at the words that contributed to this atheism prediction, we have words like there, edu. Edu might make sense if education correlates to atheism. And then we have these like NNTP host posting that are just nonsense. So here we can see that our model is not really doing anything, or it's looking at the wrong things. And then we would have to reevaluate our model, maybe take out these stop words, there have these host NNTP posting, so that we can retrain a model and without these words. So a while ago I mentioned that we get the raw data and we perturb it. So for text data, the perturbation is a bit different. What they do is they get the raw data, then they knock out some words, or they increase some words. And what that does is it looks like this. Because if you frame your data this way, wherein you have each word as a column and then the binary encoded, then this becomes a very interpretable model where you can say, oh, the presence or the absence, this word attributed this much to my prediction. Just thinking, okay. And then lastly, Lime also works on image data. So for image data, similar to how in text data we break our text into words, you can break the image into superpixels. Superpixels are look like that. They are groups of similar pixels with defined boundaries, and then we can knock out superpixels and include them at one at a time. And if we do that, we can see which superpixels are responsible for our predictions, right? So we have the perturbed instance here, and it's still giving a prediction. And then we can, using this, we can say which of the superpixels were responsible for making the prediction in the image. So here we have the explanation here. We're identifying it as a gecko, a lizard, and that's the explanation. So the disadvantages of Lime. So first of all, it's computationally pretty fast, but it's not stable in the sense that you can get different answers a lot of the time based on the neighborhood of which you sample. So for example, if we have tabular data, we don't know how far away we want to sample, and this decision is something you can decide, but it also affects your results. Any questions with Lime?
So it's not exactly fast, it's not precise. That's why it's fast. I mean, using sampling points, and because of this is fast.
Okay.
So I'm saying,
sorry.
like, it's
it's
fast because it's imprecise. I'm fine, whatever,
Yeah. But the hope is that if you with enough samples you converge towards somewhere. But
right. But then probably it's not going to be fast if you're using enough or like large number of samples.
Yeah, we'll go over that.
Yeah. Mm-hmm.
Okay. So lastly, I'm going to talk about SHAP. So SHAP has its origins from game theory, where we have the Shapley values. And the way the Shapley values work is that there's a coalition working towards a goal, so we're playing a game, and there's a payout as a result of playing that game. And the question becomes, how do we fairly give that payout? And this is not related to machine learning, right? So, for example, let's say I am a consultant. My rate is like 50 an hour, and there's a consultant B. Their rate is 60 an hour, but you can get us together package deal, for 85 an hour. How do you divide that 85 an hour towards my 50 and the 65? And in order to do this, what you would do is see, you can get the proportion of which we contribute to that 80. So that my 50 plus 65, and then you get the 85 over that, divided between us, and that would be what's considered a fair payout. And that is what Shapley proposed. So he has a way to divide the reward such that it's fair. So first, the sum that everyone receives should be equal to the total reward. So similarly, when we look at machine learning, we kind of want an additive explanation wherein we can say this feature contributed this much. And then if two people contributed the same value, they receive the same reward. 3, someone who contributed no value should receive nothing. And then if the group plays 2 games, then an individual's reward from both games should equal the reward from the first game plus the second game. So what we end up with is, let's say we start with customer A, and this is a prediction on whether or not they will buy a product, right? And we say, how much did they spend on tools? And it moves them like this much. And we say, how much did they spend on online sales channel? It moves them this much, and so on. And the problem with this approach is that with nonlinear data and with feature interactions, these things can change, right? So, for example, if the model saw the online sales channel before it saw the tools, then the effect that tools gave would be a smaller effect in that scenario. Same thing, if they already spent a lot through customer service, maybe the tools doesn't matter as much, right? So what we have here is we want to test all possible scenarios and get the average to see what the effect of this tools arrow was. And this requires n factorial combinations where n is your features, right? So we need to say, let's try these 2 features together, let's add this, what was the effect? These 2 features together, we add this guy, what was the effect? All 4 features already, we add this guy, what was the effect? And that marginal contribution that this guy added is what we deem as his SHAP value. Clear? Okay. So what SHAP does is, when applied to machine learning, how do we fairly, right? And the reason why we use this fairness is because there's a guaranteed unique solution. So we say, how do we fairly attribute the reward or the prediction towards each of our features? And when you use the model, when you use the explainer, this is the Python, you get a plot like this, where you can say, hey, this variable contributed this much, this variable contributed this much. So, to your point, Anton, where you were saying that Lime is slow because you have to sample, reading the SHAP paper, what they did was, because this would be even slower, because you have your computation is dependent by n factorial, right? So if you have 100 features, you need to compute 100 factorial for each observation. So what they actually did was they went to Lime's research, and they used Lime's approximation to see when this n factorial would converge, so that they could lessen the number of times they have to sample. So, but then it's still using more than Lime. So Lime compared to this, much faster. This would be more accurate though. So if you take this guy, this plot, and you rotate it by 90 degrees, and you plot your whole data set, you can end up with a plot like this, right? And this is interactive. What time? I will show you the interactive plot at the end of the presentation. So this is our model output, and we sample this by similarity. So you can isolate a particular feature, and you can see what the impact was. So one vertical line here is one observation. So we can see here that here it's pushing the observations up. After a certain value, it's pushing our predictions down. Later on, it's pushing our predictions up again. But this is deceiving because it's not just one feature. These are all our features, and that's why we have multiple lines. Later on, I'll show a plot with just one feature. And a nice thing about SHAP is you get a summary plot like this, where you can see the direction. So if I increase, a particular variable, how does my response variable react? And using feature importance plots with like gradient boosting, you don't get this. You see which features were important. You see what was the magnitude of those importances, but you don't quite see how it interacts. Should I increase? Should I decrease? Etc. And this is what you kind of need if you want to prescribe something, right? Or if you want to evaluate your model's consistency with, let's say, expert opinion, you need this information, right? And at work, I have also seen plots where, maybe the middle will be red, and then on the left side and the right side will be blue. So like, there's some kind of sweet spot to the feature where it helps the prediction, and in some other regions of the distribution it doesn't. Same thing here. We can get the SHAP value. On the x-axis is the number of rooms. This is housing prices. On the right side is the distance to radial highways. This is the Boston data set. So in this scenario, we can see what was the interaction between those two features. I think by default, the package plots an automatic one on the right side. Whenever you request what were the SHAP values, the SHAP values for my feature. So we can see here that there is some interaction between the number of rooms and the highways. So the higher number of rooms, they tend to not be closer to the highways. And the last point is you can use SHAP for images also. So in the same way that SHAP used the line paper for more tabular data, they also use other work, deep lift specifically, and I didn't read that part, but you can also isolate what areas of the images contributed to a prediction. So I am going to show this, how do you press the escape? How do I get out?
The one that says ESC.
There's none. I don't have a Mac.
That's your first mistake.
I want to just...
No, go up and there's a button should come up. Up left, yes. Yeah, and then press the green one.
Exit presentation.
The green one. The green one.
Green
The green
one.
one.
So,
Okay, thank you. So I should mention though that I use these tools for work, and I don't know, my boss did not see value out of it. I think the output did not align with his opinion, so kinda doesn't believe in machine learning anymore actually because of me. So I got this notebook. There was another presentation on YouTube. The speaker gave his notebook, and here we can see the interaction. You can run this on Jupyter. It loads JavaScript into your Jupyter notebook. If you don't, it becomes a static image, and we can say what was, let's say, this age, something interpretable, right? So we can say, like, for this data is, I believe that the likelihood to buy something finance related, right? So here age we can say it pushed up the prediction when it was here, and then around this area it lowered the prediction. And then you can do this for each feature to see what was the impact across the distribution. So blue brings it down, red brings it up. So like here, I don't know, there's not really much I can get out of this plot. And you can also plot it against other variables. So let's say we get the age here, and we want to just get the effects. I guess this is the housing. So like, do they have a housing loan already? And are they single or married? And in general, just by poking through these plots, you can get a better understanding of your data. So yeah, that's it I have today. Any questions?
I have comments.
Sure.
So I have 8 comments. Should we start from the beginning or from the end or what?
You tell me.
How long do we
Go
have?
ahead.
Yes.
Can I make a comment quickly before
Go
you
ahead,
get your
go ahead.
comments? I'm
Yeah.
not sure. Just philosophically, interpretability is actually everything. It's not like a nice to have that you kind of add on, and maybe there are prediction scenarios where you just want to predict and you don't care. But in general, interpretability is what lets you connect what you see to some theory or to some scientific knowledge or some expert knowledge. And since you're observing a process, you're predicting something that's a result of a process, it's only by having interpretable results you have some hope to change that process. And change the process, improving the process, finding a way to help the person get the loan, finding a way to help them avoid, get probation, is among those variables that can change, is probably one of the most important things you can do in many scenarios. So interpretability is a big thing.
So in preparing for this talk, I watched a bunch of YouTube videos. One of the videos I came across was a NIPS debate about whether or not the interpretability of AI is important. And so the pro side argued, let's say we're dealing with something medical like anesthesia dosage, for example. You train it and you don't know how to interpret it. If you use the model in production, you're gonna run into scenarios where it obviously fails, and people get hurt as a consequence of that. But the counter argument, which I don't necessarily believe in, but this was the counter argument, is that clinical drug trials are done like that right now, right? Where we have something, we don't really know the effect, and we just like release it into the wild, evaluate, oh, not enough people died, we accept that, right?
This is so this is much narrower. Well, it depends, is it much or not? But this is a much narrower interpretation of interpretability. So in mathematics, very often you don't need to define the entity; you can just define a measure for it. So I don't need to define happiness, but I can say this is my ideal end result, this is my current result. The more two overlap, the happier I am. Didn't define happiness, I define a measure for it. And then, so interpretability here, it's a little bit like, what is if you change the features, if you bias the influence or whatever, if you remove the feature, or you kind of, some of this is like a random perturbation, how the whole system is going to change. It's just that. So the interpretability here, it's more about what is the cause-effect kind
It's
of black
more
box.
like
Right.
the sensitivity of the
Yeah.
model than it is about the connection with
Correct.
to
Yes,
reality.
it's the sensitivity, and presumably someone who knows the underlying science behind it, if they see this, they'll actually figure out how to interpret it. Which actually is one of the comments I wanted to make. One of the algorithms you described, it's actually the sensitivity analysis in scientific computing. It's not in scientific computing when they say you make some kind of model for like say weather forecast or virus propagation or whatever. They're based on some differential equations and so forth, right? But you need to calibrate the model, so you need some data. Usually this data is much smaller and sparser than what we deal in machine learning. But you're still actually kind of interested. How do you interpret? What is the sensitivity of this? What is the sensitivity of the parameters in the way the system is modeled? And so the perturbations there. It was this when you use the sample n, when you use the number of n. There's like a slide in which you had several. Right. Anyway, whatever. I mean, it's a minor thing. Yes, this one, the previous one. free. Yes, this one.
Okay.
So yeah, this is very similar to this so-called sensitivity analysis in scientific computing. My other comment about the nearest neighbors, you mentioned that the deficiency is the local, the local nature, but you can compute it globally, right? I mean, you can compute for every point. You can compute what is the distribution of distances, right, for the nearest neighbors, and then you can have a global measure of the whole thing and kind of judge.
The difficulty interpreting clusters, I think, generally is trying to say, okay, we know mathematically they're more similar to one another than they are across. But what is this collection of attributes that are mathematically similar? What do they mean in the real world? I mean, it happened all the time in the old technique of factor analysis, where you would attempt to reduce your multivariate data by getting principal components or something. And you can do it. You can get decent prediction. But what you got with these factors that were essentially uninterpretable because they combined age and weather and water level, and they were very difficult to put a name to. And that meant they were very difficult to connect to an existing theory.
One of the, I guess, caveats to interpretability is that if your features are not interpretable to begin with, then you won't get much mileage, right? Like if you use PCA or something like that, or you use some absurd statistics like, like some 75th quartile of this, 75 percentile of this feature, or something, then you won't get much mileage.
So, to quantify, it might not be the case. There may be some problems where you're dealing with like some low level, let's say, indexing inside of a database. You can apply like machine learning and find that instead of using classical indexing, you could use some kind of machine learning to retrieve the data faster. And you get something that's more accurate, but you don't quite know why. You may not interpret it, but it works very well. At a level that you don't really care about it.
I'm sure there are many cases like that, but even some of the cases that seem, I think, superficially to be not about interpretability, for instance, facial recognition. I mean, do we really care how a neural network recognizes your face versus another? We do when it comes to things like disguise, masking, mistakes, because there it becomes important again.
So the false positives, how expensive it was, no?
And false negatives.
And the false negatives.
If you're jailing me on the basis of ridiculous.
Well,
Yes, that's back to
But
the criminal.
it depends on the use case. It depends on how you use.
I'm in no way ruling out the fact that there are probably many cases where interpretability is not important.
But
There are a lot that are.
one point that I think was very interesting is that interpretability is not causality. So
No, it's correlation.
It's correlation too. We're still in the correlation world. No? It's what's influencing directly. So it's more directly correlated. You have a better understanding,
But
you still know
things are not
causal.
correlated, they can't be causal. So you're
Exactly.
you're heading in the right
away.
direction.
Exactly.
this actual and some of the, I mean, general comment. You mentioned that some of this is relatively new, maybe.
Yeah.
But the inventor of random forest decision trees, he used this kind of techniques from the very beginning. I mean, in statistics we call it in general what we're dealing here with. In statistics is called non-parametric methods. And non-parametric methods, one of the main advantages that you take your test data set or whatever, right? And you randomly perturb each of the columns of the variables and you see what is the effect. And most of what I see here is just elaboration of that particular technique.
Yeah, and if you read the papers, it's more about how can we reduce complex computational time in an efficient way. So a lot of the theorems are about how can we get the minimum number of n that we can converge.
In a sense, he mentioned it too. Like you said, factor analysis. Do you mean like factor analysis from the dimension reduction perspective?
Yeah, the old well, it's
So-
an analytic technique in some cases.
Yeah, so I don't do factor analysis, but there's also different dimension reduction techniques. I would say this is what you do. You do different dimension reduction techniques, and
Sure.
then you do the same kind of perturbation techniques. So this actually, I have to say, very interesting overview. And you said you wanted more of a discussion, but I was actually more interested to see the flow of the lecture, instead of interrupting, like in the middle.
Okay.
Yeah.
I have a question. So at the beginning, you spoke about like a use case for this would be in industries that are burdened by shown to solve that problem? Because I could imagine taking this into court or to a regulator and they tell me it's all gobbledygook.
Yeah,
and it's
so-
not interpretable.
Yeah, that's a good point. So SHAP, so Lime was like NIPS 2016, SHAP was 2017. So there haven't been like cases where I would say this is used in court or in credit. And there seems to be, I saw some articles that doubt the capability of this to achieve that. So maybe we're not quite there yet, but maybe in a few years.
There's a company, American company or Canadian company, which uses commercial software to classify criminal behavior, and the algorithm is proprietary. So they basically say, no, we can't tell, and they go to courts like, why is this like, no, we can't tell. We use 120 variables. This is what we can tell. Turns out somebody actually did look at this like, hey, from this 120 variables, only 2 of them are decisive. You're basically basing you might be using probably with similar analysis like here. If you look at the outcomes and etc., it turns out from this 120 variables they claim to use for this for the criminals or whatever, alleged criminals, they basically only 2 of them are actually decisive. If you remove them, the system doesn't work. But because it's proprietary, you actually don't know what exactly is happening. This should be presumably changing, but in US in general, both healthcare and in law, they're like, so they don't share data, don't share algorithms, they think that's related to profit or related to whatever. So to some extent that's it, that's the situation.
I'm thinking of a case in English law where they tried to prove a crime with Bayesian statistics, and it got appealed to the point where they banned Bayesian statistics from British law. So if that won't cut it, I don't know that I would have a client who would be interested in SHAP or something. We have regulatory.
Not an answer to your question, but like this kind of assumes, like for example, if I get a negative credit decision and I want an explanation, there's an inherent assumption there that a human should be able to explain it. And currently, I think what the disagreement is that humans themselves disagree with a lot of things, and because of that, like it's very iffy. I think the standard for machine learning is just a lot higher than right. Like for example, self-driving, right? Even if self-driving cars are, let's say, 10 times safer than human drivers, that's still not enough for it to still go to market, right? Like fully autonomous. Like they want that. I think like, I don't know, I saw a video last year, the average human gets into an accident every 300,000 miles, self-driving was already at 500,000, but it's still not enough, right? So it's much stricter also.
I think to your point that the key event that happened in last year, 2018, is GDPR in Europe. One of the points in the law requests that the user can ask for an explanation. So that's why there was a lot of research being put into this type of tool.
Yeah, my question is more about whether this would qualify as an explanation under the law.
So at least you'll be able to tell this feature is
They'll ban it
implemented.
too. They'll ban that. Like say the FICO, FICO, how you pronounce FICO, FICO score, whatever. They do use neural networks. So they'll give you the neural network for it. Yeah, go figure it out. It's like, or like say with a random forest. Which decision trees are easy to interpret, but random forest, like they're making thousands of decision trees. They're all randomly made. And it's like, yeah, in principle they can give you a printout. It's like you can, try to see. That's a very interesting question, but to some extent, that's why you need to be using this kind of techniques, because they're model-agnostic and they're exactly this. I poke it in this direction, what happens? So what we said, at least with the parameter changing, instead of, you can see the receiver operating characteristic, you can see what is the price, the price kind of quality ratio or whatever, like true positives, false negatives, so forth. Right, what are the ratios about this? And then you can presumably judge with these parameters when they change for each of the variables, how the price of being wrong changes. It's like this can be actually it's a high school arithmetic, so it's basically relatively simple mathematics, but it is probably quite expensive to procure. Is it interpretable? I would say yes, but yes, can it be accepted in court? Maybe, right?
The thing is, GDPR is very new. I think May of last year is when it was put, and I think still people struggling to put it in place. I don't know of any very renowned case of a big case of GDPR with people.
I didn't think there was. I was curious if anyone knew of one.
Yeah.
As a comment though, I think that this can be very applicable to a lot of different areas. And I'm glad this research is going on because as AI solutions are deployed in more other industries, this question is going to come up before. How did this decision happen and why? And so we're going to want to have those higher fidelity models. And so there's some attempts to try to do them. I would still argue that the visualizations that came from particularly SHAP are kind of still hard to understand.
Definitely. And if you have a feature space like 100 features, you have 100 squared essentially interactions that you want to examine. Some of them may be correlated, so it may not also lead to something. Yeah, but at least I think at least on the local level, you can see which were the features that pushed something up or down. Yeah.
This I was doing for 10 years recommender systems for music and movies, and so music it's like thumbs up, thumbs down, right? So you don't need to prove much, like why you give this explanation. It's more like survival analysis, like how what is the probability for this song to survive in the playlist. But for movies and investments, even like it might take 50 to 20 minutes for you to see that this movie sucks or you don't care about it, whatever. So people do actually want to see explanations or proofs, but why is this recommended? And so it's basically pretty much like like what maybe you have seen Netflix before they changed the interface for whatever number of times, but they were saying, oh, because you watch romantic comedies after 8 p.m. whatever, and because you have watched this and this that movie, we recommend this to you. This actually had great response. So I applied something like that in healthcare because when you're trying to predict critical conditions for patients, I mean, you can say, okay, yeah, cold blue, sepsis, whatever, but the profile of the patient, maybe like say vital signs and etc. Maybe the physicians, they can actually read that, but the nurses, they don't operate in that way. They're more like, yeah, this reminds me of a patient 2 weeks ago, or this reminds me of a patient 2 months ago, or whatever, right? So basically, giving explanations, this person, it's like that, but it was because you had cases like that in the past you have seen. This is our explanation. In a sense, for this kind of situations, I'm forced to have 2 classifiers or 2 recommenders. One is for explanation purposes, the other is to do the actual work. So the one which predicts, you cannot explain, it's like say neural network or whatever. But then the other one, it's simpler. And so I get like simple decision tree. Simple decision tree, after you have found or what recommendation you want to give or what prediction you want to give, you give it to that simpler algorithm and it can give you an explanation. It's not, I mean, obviously it might give you an explanation for some others, right? But you already have a successful candidate according to something else. So this is just about explaining the variables. And it has worked reasonably well, but basically in the low stakes scenarios, that's why I wanted to do it to kind of move to industry and healthcare. In healthcare, it worked reasonably well, again, but something Kevin mentioned, you just cannot let people die in order to see how successful you're classified.
Can't do true experiments.
But with some of the other situations, you need to quantify what is the price of being wrong, or what is the price of being right? And so ideally, this is how to some extent the explanations even matter less, but bosses like yours, they do respond to economical measures, right? So it's like I cannot explain it, but I can tell what is my prediction for this to be wrong or not. What is my prediction? The money you're going to spend if you're wrong about this.
So one of the interesting applications I've seen out of SHAP also is that they can use it for monitoring. Like if you deploy a machine learning model in production and you monitor which of your features are corresponding to that, to your like which are your predominant features, you expect them to be the same over time. If something goes wrong in your ETL pipelines, you'll see a change that this feature is contributing more, whereas in the past it didn't. So there has been some use of it for anomaly detection, for like wrong data transformation detection also. Oh, yes.
I think there's a lot of prior art in statistics and econometrics because all the statistical models tend to have fewer variables than machine learning models. When you get a complex model of the economy, you've got a whole bunch of interrelated equations. You have a large number of variable problem again. And so when I was working at Chase Econometrics, they do simulations of the model and sensitivity analysis to see which variables, when you move them, cause the biggest output effects.
Yeah, I mentioned something like that earlier. When I talk about scientific computing and sensitivity analysis, I meant exactly this. And yeah, in statistics, they just they don't know how to deal with more than 3 variables or whatever. It's like and to some extent, machine learning, we're supposed to embrace dimensionality. We don't, we actually do want lots of correlations, lots of variables. We want to introduce even more, correlations and etc. Now this actually is good to produce good predictions and probably measure it with receiver operating characteristics and so forth. But for explainability, it's just considered to be of second importance. So it's.
So,
Just 2 announcements. Is this still working? Okay, 2 announcements. We're going to the bar, right? Carbon Kel.
yes.
After, if you want to join. And then second, for the volunteers, we are expecting the deliverable due tomorrow for our advisory panel to go over it. I see a couple of you here. Just a reminder. Right, thank you.
All right. So great discussions. If you'd like to join us.